Welcome to SLO6 video number 2 on the mechanism of the so-called Grignard reaction. So last time we met, or you watched a video of me talking awkwardly in an empty room, this is a little disconcerting, I already miss you guys. We introduced this idea of a Grignard reaction, where we saw that a new carbon-carbon bond was formed between an electrophilic carbonyl-carbon center and a carbon that we had made nucleophilic through the introduction of metal. So what I'd like to do quickly here is go through the reaction, or the mechanism of the Grignard reaction. So we'll basically assume that we already have the organometallic compound, that we'll already have the carbon-magnesium bond in what's called a Grignard reagent. We'll talk more about those in video 3. And what I want to think about with you is how the actual electrophile nucleophile chemistry works. So we'll choose a very simple ketone. We'll use acetone as an example. And we'll also think about a relatively simple so-called Grignard reagent. So we'll use the same one that we used in video 1, where there's a methyl group, which I'm going to actually write in blue, bonded to a magnesium and an iodine. So those are my two reactants initially, and I want to think about how they'll interact with each other. So just like we've been doing all semester, we're going to assign roles. So you would all be rolling your eyes at me if I even asked you at this point what the electrophilic site is. It's definitely going to be the carbonyl carbon, and like we established in the last video, it's the carbon of our Grignard reagent itself, the carbon that's bonded to the metal, that's going to be nucleophilic. Right? Remember that this carbon is partially negatively charged because of the fact that the carbon-magnesium bond is polarized toward the carbon. Okay, so if I've established these two sites, I want to try to connect the electrophilic center to the nucleophilic center, but we have a problem in that there are no lone pairs on this carbon, right? I don't have anything that I can use directly as a nucleophile, but we've seen this before. We've seen this with both boryl hydride and lithium aluminum hydride, that electrons within a relatively unstable bond, like a carbon-magnesium bond, can themselves be nucleophilic, right? So we're actually going to use the electrons from the carbon-magnesium bond to start what looks like an addition. That's going to involve forming a new carbon-carbon bond and breaking a CO pi bond, right? So this is part of our bond counting from video 1. So if I follow these steps, it looks to me like I should have a new carbon-carbon bond, 3 different methyl groups, thus the color coding, and 1 less CO bond. Okay, so if I started out with 2 lone pairs, hopefully those are visible. Yep, I'm actually watching myself while I record this. This is a very classy operation. I'm now going to have 3 lone pairs on the oxygen, making it negatively charged. And I'll have my new carbon-carbon bond, which I'm going to show in red, to the methyl group that was a part of the Grignard reagent itself. So there we go. This is an addition. We've seen this a million times this semester so far. And anytime you think about an addition, you think about, well, an elimination, right? So I would want to think about whether I could eject any of the groups from this structure, which looks something like a tetrahedral intermediate, but I'm not really seeing any good leaving groups. I could eject any of the methyl groups to make CH3-, which is a very unstable anion. So here the addition happens, and then we just stop. Yeah? And this species will persist until the water workup. Just because I want to try to connect this mechanism to what you saw in video 1 and what Grignard discovered was forming in the reaction that now carries his name, we also need to think about the magnesium, right? So if we look at what's going on here, the electrons are basically staying with this carbon into the new carbon-carbon bond that's forming, which means that the magnesium itself is becoming positive. So I have effectively like an MgI cluster of atoms where the iodine is -1 and the magnesium is +2. So the overall charge for this collection of two atoms is +1. So I have essentially an ionic interaction between the oxygen here and the magnesium, and that's persistent. So when we actually introduce water, and this is part of our workup, we then need to think about what happens here. We've again seen very similar kinds of chemistry when we went through the mechanism of lithium aluminum hydride reductions of carbonyls, where we have these stable oxygen anions that are so-called quenched or destroyed, or Ariana said occupied, I kind of like that still, until we actually introduce this water. So oxygen minus could be nucleophilic, it could also be basic, and I'm introducing a very weak acid, water, where it would be possible for water to be deprotonated by the O- in our mechanistic intermediate, which should form a new OH bond. So that bond there. We've still got our new methyl group. I'll keep color coding it in blue so it's easy for us to keep track of. And it looks to me like we'll have OH minus forming, so basically the conjugate base of water. And you'll still have I and magnesium. So we have something that looks like this now. So we made our tertiary alcohol. So our mechanistic features, which you do not need to memorize, but are helpful for actually being able to very quickly predict what will happen in Grignard reactions involving different kinds of electrophilic carbonyls, are that this is an addition, that there's no elimination if there's no good leaving group, and finally, that we're using a weak acid like water to quench a negative charge. So that's only working because there's so much water. You would look at the pKa of the alcohol here and think it's about 15. The pKa of water itself is about 14. So this acid-base chemistry doesn't really have like a preferred side, but if I've got like tons of water relative to this anion, I basically drive the protonation all the way to the products, right? So we have a water workup where water is an acid. Okay, so those are our mechanistic features. Again, direct analogy to what we saw with lithium aluminum hydride, even down to this idea that we would want to actually do a workup rather than mixing water in directly. And we'll come and talk more about that in video 3, where we start to actually talk about making Grignard reagents, as well as using them to perform specific kinds of Grignard reactions.